4.7, number 348. Where is y equals 5 minus 2x closest to the point 1, 1? All right. I'm trying to draw a picture and explain what this is talking about. All right, so we got the line y equals 5 minus 2x. It should have a y-intercept of 5 somewhere here, and has a slope of -2. So therefore, from this location, we should go down 2 and to the right 1. We'll be on the line again. Down 2 and to the right 1. Down 2 and to the right 1. We do something like this. If we just connect the dots, we'll have the line we're talking about for the most part. All right, that's reasonable. Just to illustrate what's going on here. Again, this is not the method. I just want to explain how exactly to envision what's happening as we do the problem. So 5 minus 2x is here. It's that set of points along the line, and then we have 1, 1 right there. 1, 1. All right. So on this line, we have many points, and one of them is closer to this point than all the other ones. If we start taking random points in the line to see how close they are, right? We take a straight line distance. Right, between the two. Another one here maybe. So this is obviously closer, right? The straight line distance is smaller, right? The distance is smaller here than it is here to get from that point on the line to this point 1, 1. And eventually work our way down to this one, which looks like it's probably the closest, right? Which means the smallest straight line distance. If we start moving past this point on the line further down, then we're going to be further away from the point 1, 1, and the distance between the line and that point will increase. So that's even farther, right? So therefore, over here at this point, it looks like we have what we want. We should be trying to find this location, right? Find that point on the line. And again, what is that doing? This point on the line minimizes the straight line distance between 1, 1 and points on the line. This one has the minimal distance. So we should try to construct a distance function, right? We need a function that describes the distance between points on the line and the point 1, 1. We should try to minimize it. So it turns out that we do have a distance function. I don't think about it as a function so much, but we have a formula at least. Right? The distance formula looks something like this: x2 minus x1 quantity squared plus y2 minus y1 quantity squared. You take the square root, right? And that's the distance between any 2 points in the plane. We'll call the 2 points x1, y1, and x2, y2. In the plane. All right, so that's the formula for it. So how do we use this formula in tandem with the idea of minimizing the distance? So for one, we have, in a sense, x1, y1 right here, right? That's 1 point. So I could fill in x1 here with the value of 1, the first coordinate for this point, and y1 with the second coordinate for this point. We have a particular point here, x1, y1. question is, what's x2, y2? Well, that's going to be the points in the curve. But I need to leave that abstract. I don't want to pick a particular one and just simply measure the distance between that particular point and this one and start trying random guesses in there. I want it as a function. So what I should do is use x, right? The independent variable here is my x2, and then the whole expression, right? This is y here. This is y2, right? So this is a second point. It's really a bunch of points, right? In the plane, right? So this expression x2, 5 minus x2, or you can even just leave off the subscripts, it doesn't matter, but I'm going to have them for a second here. So x2, 5 minus x2, that's going to be this set of points along this line, and I can leave it in this abstract form, and it talks about now all of the points in the line, not a particular one.